A cylindrical air drum is 2.25 meter in diameter with plates 1.2 centimeter thick. The efficiencies of the longitudinal and circumferential joints are respectively 75% and 40%. If the tensile stress in the plate is to be limited to 120 meganewton per meter square, find the maximum safe air pressure. Here the options are 0.96 megapascals, 1.024 megapascals, 0.512 megapascals and 1.92 megapascals. So here we know that the circumferential stress and longitudinal stress induced in the cylindrical air drum are thin cylindrical shells. The circumferential stress is given by PD by 2T. But here we'll have to consider the efficiencies of the joints also. Here the circumferential joint is failed due to the longitudinal stress, so that here the longitudinal efficiency of the joint should be considered in the circumferential stress, and coming to the longitudinal stress we will have to consider the circumferential efficiency, that is 40%. And here first substitute all the values in first equation and we get here sigma c into 2t into the efficiency due to the longitudinal joint and d. So which gives a value of here sigma c is limited to 120 meganewton per meter square, and here thickness of the joint is 0.012 meters or 1.2 centimeters, and the efficiency of the longitudinal joint is 0.75, and here the diameter of the drum is 2.25 meters. So from this we get the pressure is 0.96 meganewton per meter square. Now consider the second equation, that is longitudinal stress, so which gives sigma L into 4T into circumferential efficiency by D, which gives a value of 1.024 meganewton per meter square. So here we have two values, one is 0.96 and another one is 1.024. But if you use 1.024, definitely the compressive stress or circumferential stress induced in the joint, induced in the cylinder, will be crossed the limited value, that is 120. So that we will have to use the lower pressure, that is 0.96 meganewton per meter square, and the right answer is 0.96 meganewton per meter square. And in the options, the correct option is A. A is the right answer. Determine the maximum bending moment value for the following simply supported beam of span L. So here a simply supported beam carrying uniformly varying load from 0 to W from the right support to left support, and here the options are minus WL by 3, WL square by 9 root 3, WL by 9 root 3 and WL square by root 3. So first it is a uniformly varying load, so that we can consider any section between A and B of the beam so between A and B, consider any section XX at a distance x from the right support or from the support B. Let us say here the reactions are RB and RA. Now consider the moment at XX. So first we will have to know what is the load, the magnitude of the load at XX, that is equal to Wx by L. So here is the magnitude of the load at the section XX, and it is at a distance of x from the right support. Now we will have to calculate the reactions RA and RB. For that purpose we will have to use algebraic equation, that is all sigma V is equal to 0, or sum of the all vertical forces are equal to 0. Here we have two upward forces RA and RB and one downward force, that is uniformly varying load. So which gives RA plus RB is equal, the total load due to UVL is half into W into L. This is the total load and it is a downward force. Now consider moment about A. Take moments about A, that is at the support the moment is 0. For a simply supported beam, at the supports resistance of moment is equal to 0. Now consider MA, which gives RB into L minus WX by L into, sorry it is, sorry total load is WL by 2 into L by 3 and is equal to 0. Now RB is equal to WL by 6, and from these two equations RA plus RB is equal to WL by 2 and RB is equal to WL by 6, from these two we can find out RA is equal to WL by 3. So here we have the reactions RA and RB, that is WL by 3 and WL by 6. Now consider the moment at XX. At the section XX, consider the moment. Here we can write it is WL by 3, that is RB, reaction at B, into perpendicular distance X minus, you will have to consider the loaded diagram between the section XX and B. So here we have a portion, this is the total load due to UVL between these two sections is equal to half into Wx by L into X, half into Wx by L into X, and the perpendicular distance between the total load, that is the center of gravity of this section, is at a distance of X by 3. So here the perpendicular distance from the center of gravity to XX is X by 3. So now it is equal to WL by 3 into X minus WX cube by 6L. Sorry, it is WL by 6 because the RB is equal to WL by 6. So here it is WL by 6 and here it is also WL by 6 into X. So here the moment at the axis, but here we will have to find out the maximum bending moment. So that one can be obtained by differentiating this bending moment equation with respect to X and equate it to 0. Then we get the location where the maximum bending moment occurs. Now differentiating moment equation about XX with respect to X and equate it to 0. So which gives a value of WL by 6 minus 3WX square by 6L. Okay, and from this we can find out the X, and which is equal to L by root 3. So this is the point, the location where the maximum bending moment occurs. Now substitute this equation, or sorry, this value of X in the bending moment equation, then we can get the maximum bending moment induced in the beam. That is, maximum bending moment is equal to at X is equal to L by root 3, and which gives WL by 6 into L by root 3 minus WL cube by 18 root 3 into L. So which is equal to WL square by 6 root 3 minus WL square by 18 root 3 and is equal to WL square by 9 root 3. So here the right answer is WL square by 9 root 3, and the right option in the options is B. B is the right answer.